Now, to start understanding the nerve action potentials, let's draw this graph. Now, please concentrate over here. This can be asked as image-based question as well. Right? So, the x-axis will always represent time, whereas the y-axis is going to represent the amplitude of the membrane potential. Now, this is how a typical action potential looks like, the graph of a typical action potentials. Let's look at a few numbers which are related to this now. The first one you have to remember over here is minus 70 millivolts, right? The next is minus 55 millivolts. We'll see what is minus 90 in a bit, right? So now let's discuss what happens when I give a stimulus when the nerve cell is at its resting membrane potential. It takes some time for the response to occur. So the time period that is taken from the stimulus to give a response, the time difference between these two activities is termed as the latent period, right? See, initially there's no response. There's nothing over here, right? And then there's a response going up. So this period of no activity is called the latent period. Right. Now, this we have seen minus 70 millivolts is the resting membrane potential. Now, let's look at phase 1. Phase 1 of the nerve action potential. Right. Phase 1. What is it all about? It is characterized by the influx of sodium ions into the cell. This type of influx, however, is a slow influx. So, phase 1 of nerve action potential is characterized by the influx of sodium ions, which is a slow type of influx, and this is called local potential changes, right? When the cell reaches 55 millivolts from minus 70 millivolts, this is called local potential changes, and minus 55 millivolts is characteristically termed as the threshold potential or the firing potential, right? So please remember these two numbers. Local potential changes is your phase 1 when there is a slow influx of sodium ions, and the cell goes to minus 55 millivolts because positive charge is entering, right? Easy to understand. And minus 55 millivolts is called the threshold potential or the firing level. So, whenever the cell fires from minus 55 millivolts above, this is termed as phase 2, that is the phase of depolarization, right? This also has nothing but influx of sodium ions, but the influx as opposed to the local potential changes phase, that is phase 1, this influx is rapid, right? So this is the characteristic of the phase of depolarization. Okay. So once the cell has reached its peak firing level, it will try to get back to its resting level, and this we are going to call as repolarization or the phase 3 of the nerve action potential. How does this occur? This occurs by the efflux of potassium ions. So the potassium ions move outside and the negative charge is increased, resulting in the repolarization of the nerve cell. Now, one rule that we have to remember is when the nerve cell is trying to repolarize, it's not just straight away going to land in its resting membrane potential. It will always go and have a more negative wave like this, and then it will get back to its resting membrane potential, and this is termed as hyperpolarization, and this is stage 4 of nerve action potential, right? This is an important graph. Please try to remember. I'll just summarize all of these. So we have seen that there are certain phases in the nerve action potential. Let's look at phase 1. Let's revise what is phase 1. It was nothing but the local action potential changes, right? Local potential changes where the action potential is going from minus 70 millivolts to minus 55 millivolts. Coming to phase 2, we have seen that it is called as the phase of depolarization, right, where the cell is crossing its threshold of minus 55 millivolts and reaching its peak firing potential, right. Now, phase 3 was our phase of repolarization, where the cell is going to trying to come back to its resting membrane potential, and phase 4 we have seen that the cell always hits a more negative value as compared to its resting membrane potential, and this is termed as hyperpolarization. The cell goes to a value of minus 90 millivolts. So what is the significance of this hyperpolarization is that it results in inhibition of the cell, right? Because there is an influx of chloride ions and efflux of potassium ions, the cell goes into hyperpolarization of a value of minus 90 millivolts and it lands in a state of inhibition. And this is characteristically transmitted by the neurotransmitter, that is GABA. So GABA is an inhibitory neurotransmitter. We all are familiar with that. Now, the usage, the applied part of this is for sedation. That is when you completely inhibit the cells, the person is sedated, right? So for sedation, what you use are the GABA agonists. GABA agonists, yeah, immediately the two names that you will remember are nothing but your benzodiazepines and the barbiturates, right? These are the two sedatives that act using the mechanism of hyperpolarization.